So now we'll take a look at a more complicated example, and this is based on an old homework problem where we basically just converted everything over so we can solve it numerically. But anyway, the scenario is that we're going to have a substation where I have 100 kV to 12.47 kV conversion. And so we're going to have some transformer impedance that's going to be associated with this. We have an existing capacitor C2 which is already existing in the circuit, and what we're going to do is we're going to go ahead and switch a capacitor in. And so we're assuming there's going to be a little bit of contact resistance in here between the two capacitors, and I'm talking just a little bit about why we would have to have something like that. If I were going to do this again, I would probably put that contact resistance in the breaker, but it's just a small amount of resistance. And so the transformer has a reactance of 8%. We have an existing 600 kVAR capacitor. We're going to switch in an additional 300 kVAR. That's 300 kVAR three-phase, so that would just be 100 kVAR per phase. And let's assume this is a Y-connected solidly grounded system. So what I'm assuming in this case is I can just simply look at one phase. I don't have to consider the other two phases. The switching is going to be such that the switch is going to occur when we have 5 kV. This is going to be a line to neutral value at the bus and increasing. And we'll assume that the switch capacitor bank, this bank right here, doesn't have any initial charge that's associated with it. So anyway, what we need to do is we need to figure out how to model something like this EMTP. And when we do simulations, what we'll see is there are situations where we might want to put capacitors in parallel, we might want to put capacitors in parallel with a voltage source. Maybe we put inductors in series, or we put inductors in series with current sources. And when this happens, we just have to be really, really careful, because let's suppose if I'm switching this in when the voltage at this particular bus is 5 kV, well, that means we have 5 kV across this capacitor as well, right? If I were to switch this capacitor in, and it's going to have a value of 0, then I'm going to have some conflicts as far as boundary conditions in this case, because I can't have two capacitors that are connected directly together and have this capacitor be at 5 kV and have this capacitor be at 0 kV. Something has to give, right? I can't ideally have that. And so this is where you would typically introduce some resistance in the circuit. So this isn't going to be the case. And in real life, there's always some contact resistance in there. But anyway, if you had also a situation where you had two inductances, and let's suppose this initial value were, like, say 50 amps, and this initial value were 0 amps, well, we can't be connecting these two devices together in series either, right? Because the initial conditions wouldn't correspond to each other, right? There'd be a conflict. So again, when you're doing simulations, one thing to check out is, to see if you've got parallel capacitors, if you have series inductors, and make sure you're not going to have an issue with the initial conditions. So anyway, that's why I put that resistor in the circuit. We can't theoretically, if we have two capacitors at different voltages, we can't theoretically just put them together in parallel. All right. So anyway, that's just some comments I wanted to make on simulation constraints. Is, whenever you see this situation, this should raise some flags. If you see this sort of situation, this should raise a flag. If you see this type of a situation, that should raise a flag, because that voltage source, if it's ideal, is going to have a voltage across it. That capacitor at a different value, you can't throw the switch there. And then the other situation would be if I had a current injection source and I was switching into an inductor. You know, I can't do anything like that either because I have the current one value. The instantaneous value for the inductor is going to be something else. So we need different sort of tricks, like putting in series resistance in order to make this work. This is why in Matlab, in the power system toolbox, and in PSCAD, we've got what we call the on resistance and the off resistance. It kind of helps deal with these types of cases right here. So anyway, if we build the equivalent circuit, basically we're going to get these particular values, or these particular topologies right here, where I've got the source, I've got the inductance representing the transformer, I've got the original capacitor in the circuit, I've got the capacitor I'm switching in, I've got a resistance in there to kind of help me connect these two capacitors in parallel. When I do this simulation EMTP, what I need to do is I need to replace the inductors and capacitors with their equivalent EMTP models. And so again, for the inductor, I've got this model for the inductor using trapezoidal rule. It has an equivalent impedance of 2L divided by delta T. It also has a current history term. I've got the model for the capacitor. It has a equivalent resistance of delta T over 2C2. It has a history current, and I've got a similar model for the capacitor we're switching in. And what I'm doing in this particular case is I'm showing this as circuit once this particular switch is thrown is what we want to do the computations for. I'm just going to go ahead and give you all the different values for the simulation. And so when we work this through, what we basically figured out is in order to get that 5,000 volts at the capacitor, this needed to be the point of wave. We needed a point in a wave of 29 degrees. The inductance turned out to be 2.2 millihenries. C1 and C2 are these values in microfarads. Remember that this is a single phase equivalent, so I'm taking those three-phase values and converting them to basically the legs of a Y equivalent capacitor bank. And then the initial values turned out to be that this was the capacitor voltage initial value for the switched in capacitor. This was the one for the capacitor already in the circuit. And that initial value of current for the inductor turned out to be 34.2 amps. And so in order to set the simulation up, you've got to have these initial values. Now, where are these values going to come from? It comes from some pre-switching calculation. So again, you could maybe do this by hand using like phasor analysis, or if you had like a power flow program, you can get these from a power flow program. The interesting thing about this particular circuit is there's actually two different transits which happen here. There's a first transit, which is basically those two capacitors, once they're connected together, there's going to be a rapid transfer of charge through that resistance. So the time constants associated with that turns out to be the resistance times the parallel equivalent of the capacitance, which has a time constant of 3.35 times 10 to the minus 7. So it's a very rapid transfer of charge. It just occurs very, very quick. Once that transfer of charge has occurred, then what you have is you have kind of like a second oscillation, which is due to the interaction between the inductance in the transformer and the two capacitors in parallel. Remember, capacitors add in parallel. So then the effective capacitance is C1 plus C2, and then we're going to have a transit ringing frequency associated with the capacitor switching now on 1 over the square root of L times the quantity of C1 plus C2. So the frequency of oscillation associated with this is going to be 5,440 radians per second. As far as the period associated with this is going to be 1.15 times 10 to the minus third second. So if I'm primarily interested in capturing what's going on with the capacitor switching operation as far as the ringing frequency, I need to have a time step that's going to correspond to this value. However, if I wanted to get this rapid change of charge captured, I've got to have a time step that corresponds to this. And you'll actually see when I run this in PSCAD as a follow-up, what kind of difference the time step's going to make. So anyway, these are the parameters that we have to get all kind of figured out before we run the simulation. So what I'm going to do is, once I have this model in EMTP format, then I've got two Kirchhoff current law equations to write. I've got one for node number 1, I've got one for node number 2. And basically what I'm going to do is I'm going to write these Kirchhoff current law equations out. I've got the current coming out of node number 1, so that's expressed in this first equation here. And I got the current coming out of node number 2. And note this is all in terms of the voltage that I want to solve for, plus the history expression for the current, as well as any type of forcing functions that would be associated with the circuit. So the only forcing function we have in this case is Vs. I equate the coefficients, so I basically get all the terms for V1 together, all the terms for V2 together. This term for Vs, I put this on the right-hand side. All these history terms, I get these over on the right-hand side. And now what I've got is I've got something where I have an admittance matrix. So these are the admittance matrix terms like Y11, Y12, Y21, Y22. And then I've got the terms for the small current, and I've got the terms for the historical current, which you denote by the capital letter I. Right. So anyway, this is what you'd have to go through first before you actually code this up. And what I would want you to do in a homework is, instead of just jumping right to the code, I would want you guys to show me where you got those equations for. So you'd actually have to do some by hand analysis before you get the code set up. Not only in terms of getting the matrix values, but also trying to figure out what these initial values are. Because the EMTP simulation approach won't give you those initial values. That's something you would have to calculate on your own. Okay, so not only do you have these equations for voltage, but for the active elements in the circuit, you've got the history terms that you would be calculating. You've got a history term for the series inductor. You've got history terms for the two capacitors in the circuit. Then once you have the voltages update, and once you have these history terms, then you can go ahead and you can update the branch currents as well. And we need to have these branch currents for the next iteration, because that's part of what we need to calculate the history terms. So now we get into writing the Matlab code for this, and I'll give you guys a copy of this Matlab code where I've got the parameters entered in. I go ahead and do some of these time constant calculations within the code here, because basically what I'm trying to do is I'm trying to figure out what to do for a time step. And what I'm going to be doing in this case for the time step is actually going to set kind of a small time step up that would correspond to this, to capturing this inrush term, if that would be something we would want as interest. And then what I'm going to do is I'm going to run this out for looking at 50 cycles of the high frequency, because I want you guys to see how this superimposes on top of the fundamental. So note in this case is I'm not assuming that the voltage source is modeled as a DC value like you would if you're working it by hand analysis. We want to get a more accurate result in this case. So for the trapezoidal rule, I've got to have the initial values for all these different elements. And then I would go ahead and set my first value for time equal to the 0. And note that I'm using an index of 1 to represent time equal to 0. I go ahead and I put in a point of wave number in here. So what this is going to do is this is going to give me um, the initial value for voltage at Vs. And then what I'm going to do in this case now is I'm going to get the initial conditions for the branch currents. And so this is going to be IS1, I20, and also I10. So I'm getting all the different branch currents as well for the very beginning. Now what I do is I calculate my admittance matrix using the terms we had in the previous slides. And now I can go into my iterative loop. So initial time is going to be 0. I'm going to run this thing as long as time is less than my desired sim time. I go ahead and increment time, so that I'm going to get the values for time corresponding to delta t. I update my voltage in this case. Then I calculate all these various history terms, the capital I terms, using the formulas we had in the slides before. I go ahead and I put this into a vector. So this is actually the current vector, the total net current vector in this case. So where I had YV before equal to this small I minus this capital I, basically both these terms combined together now are represented here. And then what I'm doing now is I'm going to solve YV equal to, I guess you can call this Y equivalent. In this particular case, instead of solving Ax equal B directly, what I'm doing is I'm inverting Y in order to give me kind of like an impedance matrix. Then V is equal to Z times I, and then I can pick the values out for V1 and V2 from this voltage vector. So once I've got the voltages, I go through and I update the branch currents. And then if I'm not done yet, then I go back up to the top of this loop. So you see I basically have a while loop where it just keeps iterating and iterating. And once I'm done, got the final solution, then I can go ahead and plot things out. So if I look at the results, these are the results shown right here, and I'm just plotting the voltage in this case. So what I've got is I've got in kind of brown or orange, I've got the original forcing function. And then when the capacitor switches in, what this does is it basically superimposes a transient on top of this. So this is going to be basically the impact of switching that in. Since I have very little damping in this circuit, it's going to take a long time for this transient to decay. But basically what I'm really interested in is what kind of stress is this going to put? And you can basically see when you superimpose this on top of the forcing function, basically what you see is you see some additional stress which is going to be put on, say, like a customer load connected up in parallel at this particular point in time. All right. So anyway, this is what we're interested in looking at right here, is we're interested in looking at what that overvoltage is going to be with respect to what it would be during normal situations. If that's going to cause a problem, then we could do different things to fix that. For example, we could put a surge suppressor there that's going to tend to clamp that higher voltage. So it's not really that much of an overvoltage in this particular case, but it is causing a little bit of an overvoltage. Okay. Now, one thing when you are running EMTP, as I mentioned before, it's got a little bit of a history in Fortran. And so in the pre-PSCAD days, before you had this nice interface, what you'd have to do is you'd have to actually format this in such a way where Fortran could read it in. And what I'm showing you here is an old punch card format, where this is associated with the 80 columns you'd have on a Fortran card. And so you'll note in here that I've got a comment line that, hey, has 80 columns associated with it. And what you would have to do is you were allocated certain columns put in certain values. So like the fact that you had a capacitor, let's say, you would have to put the thing within certain columns. If you have the size of the capacitor, that would have to fit within certain columns. And the thing that was kind of a pain about this, if you didn't get the values to line up correctly in the columns, then basically the EMTP code would misinterpret your values. So anyway, you would have things like time steps in here, and you would basically define what you want your bus names to be, and then you put in all your element values, and you would basically define your source. You know, here's like the source amplitude and the frequency, and you put in the start and stop times for your sources and things like that. But anyway, it's very kind of cumbersome. But this is the way we used to do things. Now, the reason I'm bringing this up is if you go to some textbooks, and they're kind of older textbooks, they may still have the cases in terms of this older style Fortran input. And so you may have to know how to pull values out of here in order to redo like old simulations. And some engineers have been using like EMTP for a long time. They still may use this format because they're very, very familiar with it. So rather than using the graphic interface, you'll find people that got these simulations running they've been using for years and years and years. They're still in this old Fortran input. So if you see this right here, just realize that this is from an older version of Fortran. The simulation is still going to run just fine. But this kind of corresponds to the old way we used to have to put values into an EMTP program. So let's take a look at a PSCAD simulation, and I've got this posted up on the site as well, so you guys could take a look at it later. So I've got this set up to run, and basically what you see is when the voltage gets to be 5 kV, then basically the second capacitor switches in, and then what we see across this capacitor is we see this ringing value of voltage right here, and that's going to be the same as what a customer would see across this particular bus. So it matches up pretty close to what we got doing it with our little Matlab EMTP simulation. Something else I've also showing in here is what's the inrush between the two capacitors when the circuit breaker switches in. And what you can do in EMTP is if I open up this circuit breaker, you can see instead of having to put a second current measurement in here, that I can go to input output variables. I basically give this breaker current a name, ICB, and then basically what I can do now is I can plot this. And so for the elements, you usually have the ability of going to internal output variables, giving a name to one of these currents or breaker status or voltage, whatever, and then using that as well for a plot. Note in this case that this is giving me kiloamperes. And so what I can do is I can then link this to a measurement, and I can drag and drop it into a frame, and that allows me to get a plot. And what's kind of interesting about this is I get a current peak value. I mean, it doesn't last for very long, but basically it goes all the way up to like 30 kiloamps. And so what's sort of interesting is we've got potentially a very high stress situation right here where we basically got this current rushing through the circuit breaker as soon as the circuit breaker is closed right here. You don't see the current after that because of the scale. I mean, it's drawing current afterwards, but the current's so small it looks like it's going to be zero. So anyway, that's just one I want to kind of point out in this case. That in real life, you know, we got these very, very fast transits, and unless I set my plots up with really, really small time steps, I probably won't even see this right here. So anyway, to kind of wrap things up, one thing you could also do is Yeah, I should have left this up. If you were going to go and you see you've got tabs on here, you see you've got things like Fortran and data. What this is showing you is some of the Fortran artifacts still involved in running this simulation. So this is why you had to load these Fortran compilers on, because EMTP is still making use of Fortran. And so anyway, this kind of shows some additional stuff going on with the Fortran, and this actually shows you some data. It's not putting everything into this particular format, but you still create some data tables which are kind of similar to the old card format in terms of values corresponding to certain columns, like on a card, let's say. As far as references, oh, one more thing. Another thing I did too is I put this into a spreadsheet, and I'll go ahead and make the spreadsheet available to you as well. The reason I put this into a spreadsheet is, once you get out of school, you might not have access to Matlab anymore, and so sometimes it's kind of nice to be able to run things in a spreadsheet format or run things in Python, let's say. So if Excel's the only thing you know, let's say, or if you're very, very familiar with it, you can also code this thing up in Excel. The only problem is that it involves this matrix calculation. And so I kind of set this up where I was converting Y into Z, but obviously this isn't really going to scale up to much larger programs, because if you had like 100 elements in your program, it may not be that convenient in Excel to be solving a system of like Y equal I, where Y is going to be like 100 by 100. But anyway, at least for small scale, you could still do this. So I'll just put this up on the website as well for those of you that might just have a small circuit. Maybe you just have a second order circuit rather than going to PSCAD or Matlab all the time. You just might want to have something hard coded up in Excel. So anyway, this shows, in the spreadsheet that you had to have this really small time step to kind of capture, I guess, what you call this intercapacitor transit. You can see in this case you got one capacitor at 5,000 volts, the other capacitor at 0 volts. And then basically the capacitor at 5,000 volts, the voltage decays really fast. The one at 0 volts, the voltage jumps up pretty fast. And then eventually those capacitors are roughly at the same voltage. So anyway, as far as references, for EMTP, there's actually a wiki site for EMTP, has a little bit of information. They still offer an open source version of EMTP, and this is done through the Alternative Transits Program Group. A little bit more of a European organization, but there's a website where you still have people adding to the model and still using it. They have a lot of their own tools as far as graphic interfaces and things like that, and then you would become a member of this and you can get access to this freeware code if you want to think about it that way. So if you really wanted to scale stuff up to a large system and you didn't want to get a PSCAD or EMTP RV license, you could always run ATP, right? It basically would have the same capability as the other EMTP codes. PSCAD is a program we're using, and so here's the website for PSCAD. And then for the other version, which kind of stemmed from the EPRI thread, you have EMTP RV as well. If you're interested in looking at the original Dommel paper also, here's the reference for the original Dommel paper, and you can see this was published in 1969. All right, so I think this then is what I want to talk about for EMTP approach, and what we'll do for the next lecture is we'll get back to looking at some other transit cases then.